So the first thing I want to do tonight is talk a little bit about your project. Because look, what we have left to do this semester is you got to get this capstone project needs to be done. Remember, it's going to be due on that Friday, the last Friday of classes. We'll have a couple more homeworks. No more tests. The last thing is your final. So we're about there, right? You got the capstone, you got the final, and maybe 2, maybe 3 more homeworks. More like probably 2, depending on how things go. So I wanted to come back to this. Remember, we looked at problem 1 where you're just going to make the graphs depending on what kind of variable you have. And this problem 2 is sampling. You know, we're going to talk about choosing simple random samples here with Minitab. In the survey, the data, the variable age is the current age reported by each student. Part A says type the first 10 observations from column representing the variable age into the table and use this as your sample data for part B here. All right? So it says, then calculate the mean age. Well, I don't know. I'm coming over here to my Minitab file. I'm finding age. I'm going to type the first 10. 18, 55, 18, 18, so on. Right? We're just going to put them in there. You're just going to type them right in wherever they belong here. Find the mean age. Pull your calculator out. Add those 10 numbers up. Divide by 10. You'll get an average. Okay? It says identify the type of sampling method you've just used. Anybody got any thoughts? That's about as convenient a sample as you can get, and I'm going to leave it at that. Okay? It says next, select a random sample of size n. Here's what we're going to do. I got Minitab open. I'm going to calc random data, sample from columns. Right? That's the instructions on the project's telling you to do. I want to take 10, right? I want to sample 10. I want to take 2 things from them. I want to take their ID. Remember, we gave everybody a number. And I want to take the age. I need to save that somewhere. The problem tells you, put it in column 17, C17, space, C18. That's the first 2 blank columns in your Minitab worksheet. If you will click OK, it will pick them and it put them over here. So what mine just did is it picked the person that had a 750 ID. They were 18. 384 ID, right? This was the ID. That's their age. You're going to come over here. You're going to write the person's ID. You're going to write their age along with that. It says calculate and report the mean age. Take the 10 ages and average them together. Give me that. Identify the type of sampling method you have just used. Minitab has given you a simple random sample, folks. It's given you an SRS. Okay? And then what you're going to do is you're going to do part G, you're going to repeat it. You're going to repeat it 3 times. Each one time you're going to get an ID. In other words, you're going to come right back here. Minitab. You're going to go back to Calc, random data, sample from columns. You've got everything set up. Click OK. Oh, well, this time we picked 329, age 19, 464, age 18, so on and so forth. You're going to do that, what was it, a total like 4 times there? Each time calculate the average. Then it says, suppose we think of all students who responded to the survey as a population for the purposes of this problem. In that case, the population mean age for all of them is 20.658 years. Discuss 2 or more complete sentences, the differences and similarities between 20.658 and the answers you got in the convenience sample and the 4 different SRSs. I can't tell you what you're going to tell me here. Everybody's going to have different numbers here other than that 20.658 that they're giving me. Because all of us are going to have a different random sample. I understand when we all do the first 10, we're all going to get the same answer. We would hope that the random samples would give you a better estimate. That was the point in Chapter 8, right? That's what you're going to do. And then number 3, there's a 3E. If your E number, you have an E number. If it ends in an even number, you do this one. If it ends in an odd number, you do this one. Okay, they're both the same problem. The only difference is, in this 3E, for the even ones, it says question 7 of the fall 2015 survey asked students, approximately how much did you spend on books for school this semester in U.S. dollars? How much you spent on books for this semester in U.S. dollars? Everybody understand that's quantitative, right? Okay. Let's go down here. If your E number ends in an odd number, question 14 of the fall 2001 survey asked students, approximately how many times did you eat at an off-campus restaurant during the week? Is that a quantitative variable? So it doesn't matter which 3 you're doing. They're both quantitative variables. Okay? So if I come back up here to the one about how much you paid for books, Create an appropriate graph to display the distribution of the variable called books and insert it here. You're looking at a quantitative variable. What's the graph you want? The graph you want is a histogram. It says, which of the following best describes the shape? Is it skewed to the left? Do you have a tail going to the left? Do you have a tail going to the right? Or do you look like something roughly symmetric? I'm not going to do that for you. You're going to look at it and tell me. Okay? Using Minitab, calculate the basic statistics for the data collected on books. In other words, the mean and standard deviation in the 5-number summary. Copy and paste it here. I will show you that. I'm going to go to Stat, Basic Statistics, Display Descriptive Statistics. That's the basic statistics we talk about here. What do I want them of? I want them of books. I click OK. That's what you're going to copy and paste. Okay? Same thing if the other one was the number of times you ate out. You're going to use that variable. It says, choose statistics that are appropriate for the shape of the distribution to describe the center. Question. If this thing turns out to be skewed to the left or skewed to the right, how do you want to start describing its center? The median. Yeah? How do you want to describe its spread? The quartiles, right? The interquartile range, Q3 minus Q1. What about if it's roughly symmetric? Then for the center, you want the mean. For the spread, you want the standard deviation. See, it says, what statistic will you use to describe the center? It depends on the shape. Now, look, we've done this capstone for, I can't even remember what year we started that. Every time it's either skewed to the left or skewed to the right. I don't know. Well, hell, let's look. I mean, I'm not beyond, let's make the histogram. What was it? Books. Looking pretty skewed to the right to me. What about you? Yeah. Hell, it looks skewed to the right, and I got somebody out there that spent $1,500 on books. That looks like an outlier, but I still see a tail going to the right. So how do I want to describe the center here? Median. How do I want to describe the spread? Oh, I want the interquartile range. I want Q3 minus Q1. That'll tell you about the spread. Okay? What's the value of the statistic? What statistics will you use to describe the spread? Well, hell, my shit looks skewed to the right. I'm thinking I want the Q3 and Q1, right? I want the interquartile range. Look up the IQR rule in section 2.6 in your textbook. Remember, that was the one where it told us about outliers. You had an upper fence and a lower fence. Look that rule up. Are there any outliers in this distribution? If so, what are their values? In other words, don't just tell me, oh, yeah, there is. No. Check it with the 1.5 times IQR rule. All right? That's what justify your answer means. Oh, yeah, I had somebody pass the upper fence, or I had somebody below the lower fence. Okay? That's it. Now, I don't want to leave the odd people out. So, what was the variable here I was using? For this one here, it is eat. How many times did you eat out? Okay, I want to go to graph, histogram, simple one, eat. Looking skewed to the right to me again. I see outliers. Somebody ate out 21 times. What the hell was the question again? How many times did you eat off-campus restaurant during the week? Hell, somebody ate all their meals off campus. Okay. I got possible looking outliers. I see skewed to the right. You're going to check the fences. You're going to give me the median, interquartile. It's the same problem. We change the variable one, the numbers are different. Yes? Okay. Now, I'm done joking around here. That takes you through number 3. We will look at number 4 on Thursday at the beginning class, just like this, for a couple minutes. We'll look at number 5. Number 4 is a regression problem, where you have the 2 quantitative variables. You want to use one to predict the other. You make scatter plots. That's number 4. We'll look at that on Thursday. Number 5, there's a 5F. You do this number 5 if you're female. You do this number 5 if you're male. Number 5 in general is a question about a two-way table. There are two categorical variables. We want a two-way table. We want some kind of cluster graph or stacked bar graph, one of those things, right? That's a problem out of Chapter 6. Okay? So we'll look at that. The reason we need to look at that is not that you can't make the appropriate bar graphs or cluster graph or whatever, is I never showed you how to make a two-way table from the raw data. Every two-way table you have seen has been given to you in two-way table form. So we need to come up with a two-way table. See where it says create an appropriate two-way table to summarize the data, and then we start asking you probability questions based off of your two-way table like we did in Chapter 13, right? So we'll look at those two on Thursday, and then somebody to ask me, that'll take you to number 5. There's a number 6, and there is a bonus problem. Here's the deal. Number 6, we can't do that yet. It takes me a few more chapters before we can do number 6. And the bonus problem, it takes me a few chapters before we can do that. So after Thursday, the first 5, look, we've already seen all the material for the first 5. That's the point. You can do the first 5. As soon as we get to the point where you can do number 6 or you can do the bonus, whichever comes first, I will come back to this. All right? But on Thursday, we're going to look at problem 4, the regression problem. We're going to look at problem 5, which is the two-way table problem. Now, one other thing to keep in mind here. I know I went fast, I said things fast, and I didn't say everything you needed to say here. The deal is this. Do not forget, right here, I'm looking at your D2L site. The first 3 files are the ones for this semester. I have posted solutions to the capstone project from last spring, last fall, and the spring before that. Please take a look at the one from last spring just to start with. Number 2 is the exact same problem. You're taking this simple random sample. The one you took was the first 10 or whatever it is. It was a convenience sample. It's the exact same problem. Hell, it wasn't age. I don't know what the variable is. Number 3 is the exact same problem. There's a 3 E and there's a 3 O. There's an even one and an odd one. They're both there. You're going to make a histogram. They're quantitative variables. They're asking the exact same questions. On Thursday, I'm going to remind you to go back and look at the old solutions because problem 4 before, I'm thinking, or somewhere there is a regression problem, and then the next one's a two-way table problem. So you're not, I'm pointing in the right direction, but you have solutions here. Okay? I can't help myself. I'm sorry. Number 1's different. Oh, look, number 2, we're sampling. Oh, it wrote all this shit out for you. Number 3, oh, we must, how many times you washed your hands? Look, that one's skewed to the right also. Oh, we box plot. Oh, there's a 3. Oh, that must be the males or females was number 3 this time. Sorry. Okay. Number 4, look, it's a regression problem. Height versus weight. There's a scatter plot. Number 5. Shit, it's a two-way table problem. There's the two-way table right there. There's my two-way table. Oh, there's the different graphs we can use. Oh, there's an... You're not on your own here, folks. Okay? So that's the reason I'm warning you about the one from the spring. Okay? Is they are the same. Obviously, we have different students, we have different data, we have different variables. The questions are the same, so it's showing you exactly the way things you should be writing and everything, right? So I shouldn't have to say a lot here. Everybody understand, right? So this one matches up real close with the spring. Now, that's the first 5 problems. I never looked to see what the 6th one was on the spring. We're not there yet. You can do 1 through 3. I'll have a little bit to say about 4 and 5 on Thursday. That way you can do the first 5. And then when we get to number 6 in the bonus, we'll have a talk about them, all right? That's the best I can do. Now, here's where we're at in class. I think I got 7 days left and 7 chapters to do. The nice thing is, we're only going to do 2 things the rest of the semester. Now, I'm going to do it like 5 different times. But we're going to do 2 things. Okay? And we're changing parts of the book because when I get here and I'm looking at this chapter 16, all right? It's chapter 16, and the title of it is Confidence Intervals. Yeah, and they call it the basics. That's fine. It's the beginning. It's the first time we see it. It's the first time we work with confidence intervals. Okay? Now, confidence intervals is one of the 2 things that we're going to do the rest of the semester. What I'm thinking about is, this same thought I had last Tuesday. Sample, infer, back to your population. That's what we're ready to do. We're ready to take what we've learned from our sample and to infer back and to draw conclusions about your population. Now, I am on page 373. There's a little green box here that says Statistical Inference. I don't always throw out the word statistical. I always use the word inference. Statistical inference provides methods for drawing conclusions about a population from sample data. That's what statistical inference is for us. It gives us methods for drawing conclusions about a population from your sample, from information that was gathered in your sample. Now, a couple thoughts here. We had talked about this before. We're only going to have one population. We're going to take one sample, and then we're going to use our methods to infer back to try to draw conclusions about your population based off what we learned in the sample. Right? That's the deal. I had warned you. If you take a different sample, you will get a different result here, right? A different sample will provide a different result. How do we know that? You go back to the chapter about sampling distribution of X bar. Every time you take a different sample, you get a different X bar. Okay? Because of that, we cannot guarantee our results. In other words, I can't tell you whether I'm right or wrong. What we do is we use probability to say how often our methods give correct results. Translation is we're going to use probability. We're going to attach a probability to our method that tells us, look, if you did this over and over and over again, this is the probability that we would have a correct result here. Based off of one sample, I can't tell you right or wrong. Okay? Now, here's the thing. This chapter 16, confidence intervals. A confidence interval is used to estimate a population parameter. That's what we're going to learn about in chapter 16. Well, that's one of our inference methods. The other one is something called tests of significance. That is chapter 17. We will talk about tests of significance hopefully on Thursday when we get to chapter 17. Those are the two inference methods we have. A confidence interval, again, is used to estimate a population parameter based off of what you learned from your sample. And the chapter 17 is a test of significance, and I will give you its goal when we get there. Right? I don't want to give it to you now. Now, all of this confidence interval, and your test of significance in chapter 17, this is based on the sampling distribution of a statistic. Whatever chapter that was, 15. And for us, the statistic we're going to be working with is X bar. Now, here's what's going to happen. All right? This chapter 16, again, is about confidence intervals. We're going to use those to estimate a population parameter. Chapter 17, test of significance. What we're going to concentrate here on is how do we set things up, how are things done, and we're really going to concentrate on the reasoning and the language, right, in 16 and 17. And like I said, then we're going to repeat those in chapters to come. The first thing you got to get used to from here to the rest of the semester, when I start telling you, oh, look, we changed chapters, we have a new formula for the confidence interval. There's always conditions that need to be met to trust our inference. And so, for chapters 16 and 17, we have something called simple conditions. Now, anytime I start telling you about conditions, number one is always the same. You had to choose your sample with a simple random sample. Our methods are good for simple random samples. Okay? Number two, the population distribution. You know, the variable, the values of the variable among all the individuals in your population, where you're looking at one at a time, the population distribution. We have a couple of requirements on it. It needs to be normal. It has to have a mean, and it has to have a standard deviation. These are simple conditions. These are to get us started. Number three, don't know mu. We don't know the mean of our population. This is the thing we're trying to estimate with our confidence interval. But we know you do understand, right, that there are two things here. There's the mean of the population and the standard deviation of the population. What we assume through chapters 16 and 17 with these simple conditions is that we don't know the mean of the population, but we know the standard deviation of the population. So what you're supposed to be thinking to yourself now is, how in the hell can that be? How can you know the standard deviation of the population and you don't know the mean? Well, I'm going to be honest with you. You're not going to know either one of them, to be honest. We're trying to concentrate on the language and the reasoning of inference here. So instead of not knowing two things, let's just work with not knowing one. The other one's given to you in the problem, and then we will fix this later. And what I mean is we're going to fix this in another chapter. Now, here's the thing, is I'm going to be really big on the language and the reasoning here. When I get to future chapters, and you've seen confidence intervals once, I won't be that crazy about everything. It'll be, okay, here's what changed. Okay? So, this right here, not realistic. But instead of worrying about too many unknowns, let's worry about one unknown, the thing we're trying to estimate here. Okay? We fix that. Now, we're ready to try out this statistical estimation. Now, bear with me for like the next 15 minutes, because when I'm all said and done, I'm going to hand you a formula. Here's what you're going to calculate. And everything you're going to put in this little formula here is going to come out of the problem, all right? But I have to show you where the little formula comes from, just to make myself happy, okay? So, when I think about this reasoning of statistical estimation, it kind of goes with the problem here. Right? That's the way I'm going to set this up for you. Now, right on page 374, it says the body mass index, BMI, is used to screen for possible weight problems. It is calculated as weight divided by the square of the height, measuring height in kilograms and weight in kilograms and height in meters. Many online BMI calculators allow you to enter your weight in pounds and height in inches. Okay. Adults with a BMI less than 18.5 are considered underweight. Those with a greater than 25 are overweight. For data about BMI, we turn to the National Health and Nutrition Examiner, NHANES, a continuing government sample survey that monitors the health of the American population. I just read that first paragraph, that last paragraph on page 374. Now, what I want to look at is example 16.1. Okay? It says, an NHANES report gives data for 654 women aged 20 to 29 years. The mean BMI of these women was X bar was 26.8. On the basis of this sample of 654 women aged 20 to 29 years, We want to estimate the mean BMI mu in the population of all 20.6 million women in this age group. Okay, you have a sample of 654 women, 20 to 29. If they don't tell me any more, we're going to assume it's a random sample. We're going to assume we're looking at an SRS because of our simple conditions. It tells me that for these 654 women aged 20 to 29, their mean BMI, X bar, is 26.8. Here is your statistic. That's your sample mean. That's the mean. That's about your sample, that X bar. It says we want to estimate the mean BMI, mu. This is the mean BMI of all. How many is there? 20.6 million women 20 to 29. This right here, this is your parameter. That's an unknown quantity about a population. It's an unknown quantity about all 20.6 million women aged 20 to 29. It says, to match the simple conditions, we'll treat the Inhane's sample as an SRS from a normal population with a known standard deviation of sigma is equal to 7.5. Okay, here's the deal. Conditions. Those simple conditions. They're telling me simple random sample. That's a check. 2, they're telling me the population distribution is normal, unknown mean, and the standard deviation is 7.5. That's a check. And you see this part right here? That's sigma 7.5. Remember, you don't know mu, but you know sigma. That's your number 3. The simple conditions here are met. Now, here's the way the reasoning goes. All right? 1, to estimate mu, the mean BMI of 20.6 million women aged 20 to 29, we use X bar equal to 26.8. You use your statistic to estimate your parameter, always. My parameter is mu, my statistic is X bar. Now, a couple things here. We don't expect X bar to equal mu. We don't expect our statistic to equal our parameter. We want to say how accurate this estimate is. Look, here's the deal. We could just say, look, we got a simple random sample. Hell, we got a simple random sample of 654. What could you tell me? Well, we would expect, right, for mu to be somewhere around 26.8, right? The law of large numbers kicks in and says, oh yeah, remember, the larger your sample, the closer X bar gets to mu. We would expect mu to be somewhere around 26.8. That would just be a point estimate, right? Just using your statistic to estimate and be done with it. We want to do better than this. When we want to say how accurate this estimate is, we want to give you an interval. Remember, confidence interval? We want to give you an interval of numbers here around that 26.8 and say something about whether mu is in there or not. Okay? So we're going to take this one step further. Now, number 2. Here's what we know. If we look at the sampling distribution of X bar, We know something about it. The population distribution is assumed to be normal. The sampling distribution is normal. It has an unknown mean mu. Remember, it's the same as the mean of the population distribution. And its standard deviation is, remember, sigma over the square root of n. It's 7.5 over the square root of 654. Remember, it's normal with mean mu, sigma over the square root of n. I know sigma 7.5. I know my sample size here is 654. If I punch all this in the calculator, I get normal, mu, 7.5 divided by the square root of 654. The book tells me it's 0.3 rounded. Okay? That's where that came from. We got a calculator out. We took 7.5 divided by the square root of 654. I got the standard deviation of that sampling distribution being 0.3. Okay? Everybody follow what I just did. You're looking at x bar as your estimate here. We know it's going to be normal because the population distribution is normal. We know it has the same mean. That's the reason I'm writing mu down. We know its standard deviation is the standard deviation of the population divided by the square root of the sample size. Now, I'm going to give you something here. You've never ever seen me leave the problem with mu there. It's always the problem tells me mu is equal to something. What the hell am I trying to estimate here? I'm trying to estimate the mean of the population. I'm trying to estimate that mu. You're not going to see me write it in anywhere. Okay? Now, that's number 2. Okay? Number 3. You remember the 95 part of the 68, 95, 99.7 rule all the way back to chapter 3? The 95 part of the 68, 95, 99.7 rule, right? Remember, all normal distributions satisfy this. Says that x bar is within 2 standard deviations. Remember, the 95 is 2 on either side of mu in 95% of all samples. Right? Remember, we're talking about sampling distribution here. So in 95% of all the samples, your x bar will fall within 2 standard deviations of the mean. Here's what we're telling you. I'm going to draw you a picture of this. Here's that sampling distribution. Mu is sitting right here. Don't know what it is. That's the thing you're trying to estimate. But I know if I go 2 to the right and 2 to the left, in other words, if I come over here to mu plus 2 times 0.3, does everybody understand why I'm writing a 2 and I'm writing a 0.3? Your standard deviation is 0.3 and I'm going 2 to the right. And if I come over here and go 2 to the left, this is mu minus 0.6. This is mu plus 0.6. 95% of all the x bars fall in there. So this happens in 95% of all samples. X bar falls between those 2 values. Now, the picture's one thing. What I'm telling you is, based off of what I see there, in 95% of all the samples, this is true. I mean, that's what it means, right? That's what the area makes up, is 95% of all samples give you an x bar between these 2 values I got marked here. Mu minus 0.6 and mu plus 0.6. So at this point here, we've done a hell of a job. In 95% of all the samples, x bar is between mu minus 0.6 and mu plus 0.6. Hell, I got x bar pinned down. Is x bar the thing I'm pinning down here? What do I want to pin down? What am I trying to estimate? Keep that in mind here. I'm trying to estimate mu. That's the unknown parameter, right? Well, me having x bar pinned down doesn't do me shit. I need to pin down mu. Now, If you follow up to here, life is pretty good. Okay? Because I got to give you one more little thought here. Forget about this for just 1 second. Let me ask you this. If I tell you that my house, where I live, is within 2 miles of the grocery store, is it true that the grocery store is within 2 miles of my house? That's true, right? So, if x bar is within 2 standard deviations of mu, that means mu is within 2 standard deviations of x bar, right? In other words, that little flip-flop of language I just did about my house and the store really means this. If x bar is within 2 standard deviations of mu, then mu is within 2 standard deviations of x bar. Yeah? That's the only one where you have to think. Now look, I try to remember where I'm at all times. You don't want to see me solving those inequalities for mu, but if you do, you get the one down here. You see this right here? Do I have mu pinned down? Hell, I got mu between x bar minus 0.6 and x bar plus 0.6, right? Mu is the thing you're trying to estimate. Remember, we know x bar is 26.8. That was calculated from your sample of 654 women aged 20 to 29. They had a mean BMI of 26.8. So what is this? If I take 26.8 minus 0.6, I have 26.2. I subtracted 2 standard deviations. If I take 26.8 and I add 0.6, I get 27.4. Folks, there's my confidence interval. Now, this confidence interval can be written 2 ways. It's 26.2 to 27.4 in language. Equivalent to that being written as 26.2 to 27.4. I'm giving it to you both ways. I don't know how you'll see it on your test. When you turn in a homework problem for me, hell, I'll take it either way. I don't care. I just want to know that you got the left-hand endpoint and the right-hand endpoint. So we're looking at this interval, right? Here's my number line. I'm looking at 26.2 to 27.4, right? Now, the punchline is, this is called a 95% confidence interval for mu. Because remember how all this started. In 95% of all the samples, x bar is within 2 standard deviations of mu. So in 95% of all the samples, what I have circled in blue is true. That mu is within 2 standard deviations of x bar. So in 95% of all the samples, that's what I get. This is called a 95% confidence interval. There is only one confidence interval you're looking at. It's from 26.2 to 27.4. That's how you do this. Now, I didn't mention this when I started today, but I'm not showing you anything we haven't seen before. There's no new calculation here, right? I mean, we already knew about the 95 part of the rule. We know 2 standard deviations on either side. This little inequalities here, hell, I probably wrote something like that first when mu minus 0.6, x less than or equal to x bar. I probably wrote like something like that back in chapter 3. The only one you got to get in your head is, how in the hell did I go from that one to the one I had circled in blue? Think about my house. My house is within 2 miles of the grocery store. The grocery store is within 2 miles of my house. That's exactly what I just said. If x bar is within 2 standard deviations of mu, then mu is within 2 standard deviations of x bar. All right? Now, something you want to notice that I didn't say. See, there's my confidence interval, 26.2 to 27.4. I told you, this is called a 95% confidence interval for mu. It's because we were doing the 95 part, right? Did I ever say that mu's in there? Or did I say that mu was not in there? Never said that. Right? I never said that mu's in there. And I never told you that mu wasn't in there. Yeah? We did a lot of work to get there, but I'm not telling you that mu's in there, and I'm not telling you that it's not in there. Okay? Now, next step. Now, look, that's not the only one we're going to calculate. Eventually, I'm going to get a formula. I'm going to go to your homework problems. We'll work a couple, okay? That's the reasoning. That's the thought. Now, I'm going to back up here for a second, okay? It's all based off that sampling distribution. And in this case, the 95 part of that 68, 95, 99.7 rule. And then all I'm doing is I'm writing down what that 95 part tells us. You know, 95% of all the samples, this is true, and then I know a value for x bar. So then I added and subtracted that 0.6 from it to get 26.2 and 27.4, and then I'm giving you the language there. That's all. Right? There's no gigantic calculation here. It's just the thought process of how this is done. Now, here's the thing. All right, I'm on page 376. Every confidence interval that we look at in this class has the following form. It looks like an estimate plus or minus what we're going to call a margin of error. Now you notice I wrote that plus or minus. You add the margin of error to your estimate and you subtract the margin of error from your estimate. That gives you this interval, right? This interval of numbers on the number line. Now, for us, in this chapter and the next chapter, as soon as I change this, I will let you know. Our estimate was x bar. Our statistic is used to estimate your parameter. The margin of error that we were just looking at in that problem that's the 0.6. Remember, we added 0.6 and we subtracted 0.6. Look, it looks like this. We had a value for x bar, right? It's a 95% confidence interval. Can I write CI for you instead of writing that out every time for mu? Because it captures mu in 95% of all samples. That's the reason it's called the 95% confidence interval, that one we were looking at. Now, I am on the bottom of page 376. It says a confidence interval. We always talk about a level C confidence interval, okay? So, I think about level C confidence interval. Every confidence interval we do comes with some confidence level. For a parameter has two parts. A parameter, that's your unknown quantity about your population. The first is an interval calculated from the data, usually the form an estimate plus or minus the margin of error. Here's the thing. Every confidence interval we ever see in this class from now to the end of the semester always has that form, an estimate plus or minus some margin of error. Okay? And then there's a second part here, a confidence level C. Now, I'm going to make you, I don't know if you write in your book or if you just write everything down. It comes with a confidence level C, which gives the probability that the interval will capture the true parameter value in repeated samples. Now, two words, if you want to underline anything in that sentence there, probability, repeated. The only time you get to speak about probability with a confidence interval is when you're going to do it more than one time. So that level C, that confidence level is telling you the probability that you'll actually be correct when you do this over and over again. That is, the confidence level is the success rate for your method. This level C This is your success rate. It's how often you will be successful if you do this over and over again. Remember, when we do it one time, we don't know if we're successful or not. We give it a probability to tell you how often our method, how often our confidence interval gives a correct answer. Now, here's the thing. I'm on page 377. Okay? I'm actually going to write this page number down for you. Page 377. And what I'm looking at here is interpreting a confidence level. It's the language. It's the language you can use and the language you can't use. Now, here's the deal. That problem we did about the BMIs, we had this as our confidence interval, right? We had a level C equals 0.95. I write it as 0.95. If you write it as a 95%, nobody's going to excite. Remember, this is a probability, right? This confidence level, this C. We had a level C equals 0.95 confidence interval, and we had 26.2 to 27.4 that we calculated, right? That's what we did. Now, before I start looking at interpreting a confidence interval or confidence level, here's the thing. You see that interval? One of two things is true about this interval. Either mu is in there or mu is not. That's no great, I didn't take a great mind to make that statement, right? The mu you're trying to estimate is either in between 26.2 and 27.4, or it's not between those two. Everybody agree? That's not the problem. The problem is, I can't tell you which one of those two things is true. I can't tell you if mu is in there. I can't tell you if mu is outside. Here's what I can tell you. If your X bar, if your sample gave you one of the 95% of the X bars that's between two standard deviations, mu is in there. What about if your sample gave you one of the 5% outside of two standard deviations? What do you know about mu? Is mu in there? Do you know if your sample was one of the good 95% or one of the bad 5%? You don't know. So we never, ever take a single confidence interval like this and say that mu is in there. You don't know that. Right? So now here comes the language. It says the confidence interval is the confidence level is the success rate of the method that produces the interval. It tells you how often you would get a correct result if you did it over and over and over again. We don't know whether the 95% confidence interval from one sample is one of the 95% that captures mu or one of the unlucky 5% that misses. You don't know. In other words, I'm telling you, we can be completely wrong here. Okay? To say that we are 95% confident that the unknown mu lies between 26.2 and 27.4 is shorthand for saying we got these numbers using a method that gives correct results 95% of the time. So here's the language. We calculated that confidence interval. What we can say about it is this. We are 95% confident that mu, the thing you were trying to estimate, remember, that is the mean BMI of all 20.6 million women 20 to 29 is between, what is it, 26.2 and 27.4. Nowhere in that statement am I saying that mean BMI of all 20.6 million women aged 20 to 29 is in there. I am giving you the success rate of your method. When I tell you we are 95% confident, I'm giving you the success rate. If we did this over and over again, 95% of the time we'll capture it. We're not going to do it over and over again. We're going to do it one time. We're going to take one sample and calculate one confidence interval. So you can't tell me if it's in there or not. You don't know if it's one of the good 95% or one of the bad 5%. There's some things here. That's your success rate. This is the thing we're trying to estimate. That's the interval that we calculated. Every time I calculate a confidence interval for you in this class, I will write that kind of statement down. I will give you the success rate. I will give you the parameter you were trying to estimate, and I will give you the interval that we calculated. Okay? Do not tell me the probability is 95% that mu is between 26.2 and 27.4. You don't know that. You don't. Okay? Now, page 378 for 1 second. And then I'm going to give you the formula and then we'll calculate something here, okay? I'm on page 378. There's a graph here. Figure 16.2. 25 samples from the same population give these 95% confidence intervals. In the long run, 95% of all samples give an interval that contains the population mean mu. Now, there's 25 of them there, right? And you notice they got the mean highlighted there with the black line. That's the mean of the thing you're trying to estimate. You'll notice the first 4 cover mu, right? The 5th one misses it, yes? So here, 1 out of 25 of these 95% confidence intervals misses it. Anybody concerned about that? We're expecting to miss 5% of the time, and we're expecting to capture 95% of the time, right? This is the repeated part. This is the probability being 95% that in repeated samples, repeated confidence intervals, that you'll capture mu. Right? I can see that 24 out of 25 capture it, yes? There's only 1 that's off to the side there, and mu is not in that interval. Is that what we're expecting? I'm expecting if I did this 100 times, 100 different samples, 100 different 95% confidence intervals, for 5 of those 100 to miss, 95 of those 100 to capture, yeah? The problem is, give me one of them, I don't know if it's one of the good, I don't know if it's one of these 5 or one of these, I don't know. That's the point. The reason I wanted to show you that figure 16.2 is I'm trying to make sense out of, so how in the hell can you talk about probability? You don't talk about probability when you do it once. It's when you do it over and over again. If you do it 25 times, you miss 1 time, hell, we were expecting that. If I did it 100 times, I would expect 5 of them to miss. The problem is looking at any one of those, and if I didn't know what they were giving me here, I can't tell you if it misses or hits. But I'm expecting 5 to miss. I'm expecting 95% to hit. And when I say hit or miss, it means the 95 of them capture it, 5 of them don't. Now, you're going to hear me screaming to you about that little probability, repeated samples. The confidence level is just your success rate, right? You just give it to me. Me writing a statement like this, I'm not telling you that mu's in there. I'm not telling you it's not. I'm telling you. The method I just used is correct 95% of the time. Whether this one I'm looking at is one of the good 95% or one of the bad 5%, I don't know. Okay? Students usually don't like that idea. That you do all this work, and at the end, is mu in there? Hell, I don't know. Is it not? I don't know. I don't know. Okay? Now, we need a formula is what we need. Then we need to work a couple problems. So, I'm thinking about confidence interval for the mean mu. Now, there was nothing special about 95%. We can have any confidence level C. It can be 99, it can be 95. 95 is probably the most common. It can be 90, hell, it can be 80. It can be any. You're capturing some percentage in the middle here, right? We capture the middle 95%. We might want to capture the middle 99%. You might want to capture the middle 90%. Okay? Now, here's the way I'm going to attack this with you. There's something called Z star. That's a Z-score. Remember, for 95 part, we went 2 standard deviations on either side? I told you how many to go. That was your Z-score, right? So the Z-star is called a critical value. And what we want is, you want this standard normal, where all the Z-scores lives, and we want to come out here to Z star positive minus Z star this area that I want between here, I'm just going to write it as C%, right? Whatever that probability is, we try to capture the middle 95% of the middle 90%. Now, if we had to, we could find that little z. We're not going to have to. In the back of your book, there's a table C. You've seen table A before. Remember, that's your standard normal. That's where you look up z-stores. Table B was your random digits. There's a table C back here. So it's after table A and table B. I'm going to go back there and look at it, and it says table C. It's called T-distribution critical values. That's not what I'm interested in. If you'll look at the left-hand column where it says degrees of freedom, you see down here at the bottom where there's a little Z star? Everybody see that? It's the third one up from the bottom, right? Z star. You see across the top it says confidence levels 50, 60, 70, 80, 95, 96, 99. If you'll pick, let's say you want 90% confidence level. In other words, you want to know how many standard deviations on either side of the mean to go to capture the middle 90%. You come down at 90% and you read across Z star. Everybody see 1.645? That's how you tell. That's the Z you need. So here's the way I think about it. Confidence level. There's 3 that I have in my head. And then the Z star. You'll always have this table. We like 90%. We like 95%. And we like 99%. So off of that table C, the Z star for 90% is 1.645. What's 95%? Notice it's not 2 exactly, is it? What is it, 1.96? That's exact. Remember, the 95 part of the 68, 95, 99.7 rule is an approximation. If you want to capture exactly 95%, you go 1.96 standard deviations on either side of the mean. You don't use 2 ever here. Somebody wants 95% confidence level, you use 1.96. For 99%, how many standard deviations on each side do you go? 2.576. Is that right? Those are the 3 common ones. If one of the problems asks you something crazy, you got table C. You'll always have that. You don't have to memorize these. All right? So look, this is what this is telling me. If I'll go 1.645 standard deviations to the left, 1.645 standard deviations to the right, I'm going to capture the middle 90%. If I go 1.96, I'll capture the middle 95. If I go 2.576, I'll capture the middle 99%. Right? Now, here's what I'm going to do. You remember the formula we had, what we did? We did 26.2 plus or minus 0.6. I'm going to work backwards from this. Remember, this was my X bar. That was my estimate. That was my statistic. Plus or minus 2 times 0.3. That's where the 6 came from, the 0.6 came from. Well, the 2, that's your little Z star, right? Remember, we went 2 on either side. How did I get to 0.3? What was that? That was 7.5 over the square root of 654. Right? So what do I have here? I got X bar plus or minus Z star sigma over the square root of n. There is your formula for a level C confidence interval for mu. Here is your estimate. Your statistic is your estimate. This is your margin of error. That Z star, which comes from the confidence level, the sigma comes from the problem, the n comes from the problem. That's your estimate plus or minus your margin of error. Now, if I write this in red, will this help? Used to estimate a population mean, but there's more to it than that. When sigma is known. And when I say sigma is known, it's given to you in the problem. Remember, they gave me that 7.5 in that problem back there. Now, here's what I want to do. They got an example of all this. That confidence interval I just gave you, it's on page 380. It says, draw an SRS of size n from the normal population, have an unknown mean mu and known standard deviation sigma. That's your three simple conditions. SRS, normal population, sigma is given to you. A level C confidence interval for mu is the one I have written there. Look, you don't have to memorize this. You know your formula sheets that you always have, those 6 pages? That confidence interval is on there. Okay? It says a critical value Z star corresponding to the confidence level is illustrated in figure 16.3, same illustration I gave you, and it's at the bottom of table C, where I showed you they all are. Okay? What I would like to do is this. Example 16.3, that's one. What I want to do is I want to come over here to your homework problems. Okay? And I want to look on page 387. Because, look, I'm going to be honest with you. There's no reason why all of us can't calculate the confidence interval. Now, what you say after the fact is usually a little harder thing to deal with, but I'm just going to pull the information out of the problem. Everything's in the problem. So if I look on page 387, 16.19. Okay? A class survey in a large class for first-year college students asked, how many hours do you study during a typical week? The mean response of 463 students, how large is your sample here? What's n? Everybody see, this is the mean response of 463 students. N is equal to 463. X bar was 15.3. Always got to know your sample size here, folks. So n's 463. The mean hours per week they study in a typical week is 15.3 hours. It says, suppose that we know that the study times follow a normal distribution with a standard deviation of sigma 0.85. 8.5. Sigma is 8.5. You understand, they've got to give that to us at this point. They've got to tell you the standard deviation of the population. Does that normal mean anything to us? That's still the simple conditions, right? We needed normal. We need sigma given to us. Yeah? It says, in the population of all first-year students at this university, use the survey result, use this sample result to give a 99% confidence interval for the mean study time of all first-year students. The confidence level is, what is it, 99%? They want us to estimate mu. And that would be the mean study time per week of all first-year students based off of this sample. So, is sigma given to me? Yes. That means I want this confidence interval when I know sigma. I want this guy right here. X bar plus or minus Z star sigma over the square root of n. X bar is 15.3. What's Z star? I don't know. I'm going to table C, right? My confidence level is 99%. My little Z star, if you look on table C, is 2.576. So I've got plus or minus 2.576. My standard deviation is 8.5. My sample size is 463. Now, if I get this far, I have a question for you. Where'd all my numbers come from? Where'd this number come from? Was that in the problem? Did it tell me the sample size, 463? Was that X bar in the problem? Yeah. They told me the mean study time for the 463 was 15.3. Where did the sigma come from? Problem. The only one you had to look up was Z star. Did we give you a confidence level? Yeah. You notice there's 4 numbers in my confidence interval, and they're all in the problem. The Z star, you had to look up the confidence level to see what that little, how many we were supposed to go, how many standard deviations on either side of the mean we needed to go. You pull out a calculator. Anybody got a calculator? And the way I do this is with a calculator is I know, I'm supposed to read from left to right and do all the shit from left to right. No. I work from right to left. I'm going to take 8.5 and I'm going to divide by the square root of 463. Whatever I get there, then I'm going to multiply by 2.576. Yes, I'm working from right to left. Every confidence interval you're going to see me do the rest of the semester, I'm going to work from right to left. Okay? Because at 15.3 plus or minus, I need the margin of error. So I need 8.5 divided by the square root of 463 times 2.576, Tyler? 1.018. How about 1.02? Now, what you're looking at there, for all I know, that could be the answer, right? There's 15.3 plus or minus 1.02. You understand, that's your estimate plus or minus your margin of error. We can go further. If we take the 15.3 and we subtract off 1.02, we're going to get 14.28. Right? That's to the left. If I take 15.3 and add to 1.02, then this is going to give me 16.32. Right? Now, I'm going to give it to you both ways because I don't care how you write it for me. I just want to make sure on a multiple choice test at the end of the semester that you know this is 14.28 to 16.32. Interval notation, math people's notation, 14.28 to 16.32. That's your confidence interval. I pulled all the numbers out of the problem, plugged it in my formula, pulled the calculator out, and calculated it. Now, I'm not done. I know the book only asked you for what's the confidence interval. Well, there it is. My confidence interval is from 14.28 to 16.32. But I'm going to do this. We are. What was my confidence level this time? It was 99%, right? We are 99% confident. Give everybody your confidence level. Give them your success rate of your method. We are 99% confident that mu, the mean study time of all. Now, I'm not making this shit up. I'm looking at the question here, right? That's the reason I keep going back to the book. What the hell was I trying to estimate? Oh, I wanted the mean study time of all first-year students. Mu is the mean study time of all first-year students. Is between 14.28 and 16.32. Remember, that's my standard interpretation. That's my standard statement. Now, by me making that statement, am I telling you that mu is in there? No. I'm telling you if we did this over and over and over again, 95% of the time we would capture. 1% of the time we would miss it. I'm giving you the success rate. And I'm giving you the interval we calculated. Now, does everybody see there's a part B? Yeah, we like to do this kind of shit to you too. What condition not yet mentioned must be met for your confidence interval to be valid? There's three, isn't there? Simple random sample, normal distribution of your population, sigma was given to you. Well, you know sigma was given to you because I calculated the interval. The population normal, what's missing here? Anywhere did it say that this was a simple random sample? And the answer is no. They never told me it was a simple random sample. Now, that's how it's done. It doesn't make a difference what they give you. They're going to give you a confidence level. They're going to give you a sample size. They may give you the data and you have to calculate X bar. They might give you X bar. They're going to give you sigma. You ever heard the phrase plug and chug? Read the problem, pull the information out, plug it into the formula, pull the calculator out, and get your interval. Pay attention to the statements that I'm making at the end. Even though it didn't ask for it, I did that to you. Okay? Now, to me, the last thing that's in this chapter, right, is the following. Yeah, it's the last thing. The book always wants to talk about how confidence intervals behave. Now, remember, it looks like an estimate plus or minus a margin of error. Just one second. You understand, my little x bar is sitting in the middle of that interval. How do I know that? Because you added the margin of error and you subtracted it, right? It's sitting in the middle, right? It's like the locator. What controls how wide the confidence interval is? The margin of error, right? The larger the margin of error, the larger the interval. The smaller the margin of error, the smaller the interval, right? So, I want to think about this margin of error. And I want to call it something here because I get tired of writing this. So I'm going to call the margin of error M. And it's this part right here. That's the plus or minus part, right? This is the part that controls the width. Because you add M and you subtract it. Again, the larger the margin of error, the wider the interval. The smaller the margin of error, the narrower the interval is. And when I think about how a confidence interval is behaving, it's not the x bar. Hell, that's the estimate. That's where it's centered. It's the margin of error. Can I control the margin of error by changing things? Look, I'm going to give it to you like this. What I would like to do is I want to make M smaller. So whatever I tell you to make it smaller, if for some crazy reason you'd like to make the margin of error larger, do the opposite. Okay? So, one way to make it smaller is for Z star to get Z star to be smaller. Now remember, that little critical value comes from your confidence level. If you're going to make Z star smaller because you're multiplying by it will make the margin of error smaller, what you're doing is you're showing me less confidence. Look, 90% confidence, Z star is 1.645. 95% confidence, Z star is 1.96. If you're doing a 95% confidence interval and you want to make the margin of error smaller, go to 90%. Instead of multiplying by 1.96, you'll multiply by 1.645. So make Z star to be smaller means you will settle for less confidence. Well, look, you're decreasing your success rate. Can I make the margin of error smaller, the interval narrower, and be less confident, have a lower success rate? Yeah. You understand the opposite of this is if I want to have a really high confidence level, my margin of error needs to be wider because I need to be more confident that mu is in there. They're connected. 2. And I only got 2. Right? The book, if you're reading the book's going to tell you there's 3 things you can change. You can change sigma. No, I can't change sigma. Hell, that's in the problem. The other thing is make your n larger. In other words, increase the sample size. Now, I'm going to come back up here just for a second, all right? See the formula? Z star times sigma divided by the square root of n. Z star, if I multiply by a smaller number, the whole thing will be smaller. You see the square root of n's in the denominator? If I divide by a larger number, the whole thing will be smaller. Okay? So there's 2 things I can change to change the margin of error. I can change the confidence level or I can change the sample size. And while we're here, you've seen me write this before. To cut the margin of error, M, in half, you need 4 times the sample size. So, I'm not supposed to say this out loud. I can manipulate things here, right? I can change the margin of error by changing the confidence level, or I can change the margin of error by changing the sample size. If I decrease your confidence level, if I make that z star smaller, or if I increase your sample size, I will make the whole margin of error smaller. I will make your interval narrower, not as wide. If for some reason I want to increase your confidence level, decrease your sample size, I will make the margin of error larger. I will make your interval wider. That's how a confidence interval behaves. It's how the margin of error behaves. Okay? Now, here's what I want to do. I want to come to 16.8. Okay? I'm not going to do all the calculations. I'm going to leave that to you. But in 16.8, it's the confidence level and margin of error. In other words, they're going to start changing your confidence level, and you're going to see how the margin of error changes. Example 16.1 is where we started tonight. Describe the NHANES survey data on the body mass index of 654 young women. The mean BMI was X bar was 26.8. We treated these data as an SRS from a normally distributed population with standard deviation 7.5. Okay, you had N was 654. X bar is 26.8. Sigma was given to me at 7.5. You had a simple random sample. Population distribution was normal. And they gave me the standard deviation of 7.5. Those are the simple conditions they're reminding you of. It says, give the three confidence intervals for the mean BMI mu in this population using 90%, 95, and 99. Now, 90%. C is equal to 0.90. What do I need from that? In my little formula, I need Z star, which is 1.645, right? I'm reading table C. So I'm going to have 26.8 plus or minus my Z star times my standard deviation over my sample size. Agreed? It's the same guy. X bar plus or minus Z star times sigma divided by the square root of n when you know sigma. And then for 95%, warning, Z star off of the table is 1.96. You're going to get 26.8 plus or minus 1.96. 7.5 over the square root of 654. The only thing you're changing here is your critical value, that number from your confidence level. And then for 99%, Z star is 2.576, 26.8 plus or minus 2.576, 7.5 over the square root of 654. Now, all we changed in those three was the confidence level, because we want to see how the margin of error changes as the confidence level changes. What do you think happens as I go down the page here? You notice I've increased the confidence level, right? I went from 90 to 95 to 99. I've actually increased Z star. What do you think happens to the margin of error as we go down the page? It gets wider, right? As I go up the page, we have decreased the confidence level. Z star has gotten smaller, so the margin of error is getting smaller, right? That's what you're supposed to see here. It says, part B, what are the margin of errors? That's the plus or minus part. You'll have one for each one. Tyler, did you do these? We'll leave it up to them. You'll get three margin of errors, right? One for 90, one for 95, one for 99. Give the three. And what's supposed to happen is if you increase the confidence level, you will increase the margin of error. If you decrease the confidence level, you will decrease the margin of error. Okay? Now, I got your test to get back to you. Remember, they're out of 40. Look, I know we did this in one night. This is not the last time we're going to see a confidence interval, and you're going to see me read the problem and pull the information out and plug in. You have to get it stuck in your head that you use this confidence interval when sigma is given to you and you're trying to estimate a population mean mu. All right? I will keep repeating that to you. And as I work different problems, I'll ask you, do you know sigma or not? Okay? So, everybody be careful going to the house. Get your test back. We will see you on Thursday.